will be sharing his work on macro mini linear actuator using electrical fluid brake for impedance modulation in physical human-robot interaction.
So I'm P. Chaisholat from Chulalongkorn University of Thailand. For active body weight support system, sometimes we require high force actuator and also highly backdriveability in the same time. And we have two complementary strategies. We can use feedback control. We can have the variable intrinsic property of actuator, such as variable stiffness actuator. But in this paper, we present a novel concept of macro mini linear actuator. The macro actuator is high force, and then we have the low impedance unit. And for the low impedance unit, we have the mini motor that directly connect to the endpoint and also connect to the rotor of the ER fluid brake. So the endpoint already connect to the mini motor, and when we adjust the damping in the ER fluid, we can adjust the impedance at the endpoint. But if the ER fluid is completely locked, sometimes the macro always connect to the endpoint. And we also can modulate the impedance in the ER fluid brake so that we can have the moderate impedance at the endpoint. Without the brake torque, the mini motor just drive the output. So we can rapidly adjust from low to high impedance. We always have accurate position control because the mini motor always connect to the endpoint. And we have falling prevention. Endpoint drop down to hit the carrier and just no damage. And we have less energy loss because with the brake, it only dissipates energy when we have the relative motion. And in this system, we have macro, mini, we have ER fluid brake, and we have the force sensor. The video show that the brake control the impedance, and we can feel it at the endpoint. We need to build the ER fluid brake, and we suggest to use the multiple concentric cylinder design that we can have the several piece of concentric cylinder. And we can have small radius difference, and we can have high torque to inertia ratio with this design. We build the brake prototype, and we characterize it. When we adjust the voltage command, we can have the torque that track the voltage command. We can see the fluctuation in the one rotational, and it's due to the inconsistent fluid graph. And we can track the positive and negative step command with the response time less than 50 milliseconds. We can see that when we increase the voltage, the torque increase, and we can find the linear relationship in somewhere in the plot. And in the operating range of the speed, less than 240 RPM, it seems like the speed is not affect the profile of the torque. But at high speed, sometimes we see, at extremely high speed, sometimes we see the effect of the speed. And in this plot, we conduct the constant speed test, and we can study the static friction in the zero speed. The offset of the torque in forward-backward direction is static friction, and static friction is increased with the voltage. The slope of this is the damping. The damping slightly decreased when we increase the voltage. In the beginning, I want to have adjustable damping, but by this, it seems like when we increase the voltage, damping decreased, but what we can do is we can adjust the static friction. So finally, we want to have a highly backdrive, so we implement the feedback control. We have the phase lag and KDC gain, and we can reduce inertia, can reduce static friction, and for the viscosity in the last plot, we model the system with the linear second order, and we underestimate the damping with this because the model doesn't include the static friction. So I think that's all. If you have any other question, we can meet at the poster. Thank you, everyone. Yeah.